Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to day 51 of NL Math Man's Math Help Stream. We're here at the same math time every day, right? 1 p.m. Newfoundland time, and the same math channel, which is twitch.tv/NL Mathman, right? Behind me today, now we have a very nice picture again of I've been doing St. John's all week, or St. John's area at least. So that'll be my theme for this sort of calendar week, I suppose. Right? What I've got behind me here, this is from Cape Spear, right? Or out toward Cape Spear anyway, looking back toward the city. If we look there above the word include upon the right, we can see that is actually, in towards St. John's Harbor, right? Way up above the word include here. And we can see we've got some very nice colors of the water over here, right? Oh, boy, oh boy. Over here, right? And the nice greens and dark blues. And for anyone who's considering visiting the province, like for tourism or anything like that, right? These are the kind of vistas and views that you can get just outside your car. Like this is not even a hike to get this one, right? Before the one that I showed of like up on a hill looking out over, it was a significant hike to get to that view. And the one over Kitty Vitty was a minor hike. But this one you just park your car and just step outside practically, and you're seeing this kind of stuff, right? Although granted, this is a sunny day in this picture, right? So I mean, those are sometimes few and far between. You know, I've people talk about London fog, right? I lived in London and or near it, and London fog ain't got nothing on St. John's fog. It's a rainy, drizzly, foggy sort of place, right? But hey, when it gets nice, it gets really nice indeed. And we see this picture here. Actually, let me show you something. Let me compare this one to. And you'll recognize this one. This is just sort of a different angle on the same one that I had a few days ago. I believe last Friday. And you'll see there under the word stream. You'll notice how there's like these points of land that jut out, right? So we got this one here in the middle to like the left of where it says statistical right now. But the one under where it says stream, well, that is actually the same one that we see up here under the word starts, right? It's just the other side of it, right? So if we look at the other side of that peninsula, and the Avalon and the island itself is dotted with jutting peninsulas all around it, for sure. Like the villi of an intestinal tract. There we go. That's a cross-curricular lesson there for people doing biology. That's the same, sort of jutting peninsula that we see over here under the word stream, right? So this one is up. This vantage point was up on a hill, sort of over, I guess we can say the eastern direction past the city, and this is carrying on even further east. But this one here, like I said, is literally just outside the car. You just park the car, get out, and you can see stuff like this, right? So it's a very scenic piece of the world for sure. And we can see, just barely above the word include, the entrance to the harbor. The harbor that, of course, brought people to St. John's in the first place, right? That's what 1519. A map, Frere's Atlas, I believe of 1519, is the oldest recorded evidence of habitation in St. John's and a settlement in St. John's. Now, granted, definitive evidence of permanent habitation didn't we don't have until about 1627 or so, right? Which is like exactly the same time, or 1628, I believe. Like it's just barely after sort of the Pilgrims and the Mayflower in Massachusetts, right? But there is documented evidence that St. John's has been used as a harbor continuously by European fishermen since 1519 at least, and probably before that even, right? And how secluded and how sheltered and large the harbor is up there above the word include. You can see the entrance to it. That's what brought. It's one of the reasons why people settled there of all places. Of course, it was the proximity to the Grand Banks and the most fertile fishing ground in the world that fed Europe for hundreds and hundreds of years. You know, the French Empire was so desperate to maintain holdings on this incredible fishing ground that they that's why they kept Saint Pierre and Miquelon, right? Like, why is this tiny little bit of France just directly south of Newfoundland? Well, in the treaty that ended the Hundred Years' War, France just fought tooth and nail to retain some little bit of North America, or in Eastern North America specifically, so that it could retain access to the fishing grounds of the Grand Banks, which were essential in feeding domestic populations in Europe. It's strange now that we think of Atlantic Canada as being the part of Canada that's sort of suffering economically, but 500 years ago, and 400 years ago, 300 years ago, 200 years ago, even, for all that amount of time, Atlantic Canada was like the reason why massive fishing fleets were coming from Europe every year to North America. And just retaining access to those fishing grounds was of utmost importance to like the biggest, empires in Europe at the time, right? It's just a bit of a history lesson there, I suppose. Got off onto a bit of a tangent, but I do love talking about that. And, it's a nice little intro to the NL part of my NL math man, right? I got to live up to the name somehow. So I've been showing too much stuff about like traveling and things. I haven't shown any very much Newfoundland. So for the rest of this week, maybe we'll be taking a look at St. John's in the beginnings of our streams. Although I have shown the cabin, right? The cabin is NL too, of course. Anyway, today for math, I'm going to get into first. I'm going to do statistical combinations. So statistical combinations NCR. Yeah, so Calais, that is the topic that you're on to there now, and I'm going to compare those to permutations and talk about why you would need to do those. When you would do one versus when you would do the other. It's a very important part of that unit. I'm going to do radicals, NPVs, and solving. That one's going to be for Betty Ann's course, which she's preparing for a test in. And then angle properties review for Renetta's course as well, right? So, all right, without further ado, I am going to skip on over here now. I'm probably wasting my breath to say it, right? But it is significantly better for me and for all the students involved for you guys to watch live when this happens, because that way we can interact more like what we do back in class, right? The biggest reason why I did this stream from the start was not just to put my face out there on the internet yammering on about like St. John's history and photos that I've taken, because it's definitely not its own reward to be broadcasting to the internet, let me tell you. But the point of it is to have the ability to interact in real time, right? Which we don't get if we're just emailing each other all the time, right? So this way it allows me to teach as if we were in class, and allows you guys to give me feedback and say if I'm partway through a question or something like that and you don't understand, you can stop me and say, hey, can you redo that step, or can I have help with that part? Right? It's not something that's possible if we're just using sort of email and other like atemporal kind of ways of interacting. So this is Math 3101, 3101A, and this is, I believe this is Unit 2. Yes, it's Calais, right. You're preparing to do your test for Unit 1, but I did want to go on and introduce some of these topics for Unit 2. And we see over here on the side is a page out of your textbook, a very useful one. This is page 117. And this one explains in fair detail, right, the basics of what we're going to need to know about combinations. So it says here you can solve counting problems when order is not important by counting the number of combinations. And quite frequently, you'll notice that order will not be important in these kinds of questions. The number of combinations form a set of different objects where only R of them are used in each combination. It can be denoted by NCR or N over R. But don't, NCR is equal to NR like this in a bracket with one on top of another and with no line through the center. This is not a fraction, don't be fooled. This is just another way of writing NCR. Now, generally on your test and other study guide parts, we will write it as NCR instead of N over R, but it is important to know that this and this are the same. And then that's the same as N factorial over R factorial times N minus R factorial. And you'll notice the only difference then between NCR and NPR is this term here, right? So this is the difference. Right? Because just to remind you over here, let's do that in a different color as well, so that it's clear that this is a reminder over on the side. NPR PR is equal to n factorial over n minus r factorial. So what does this mean, this difference in the formula? Well, we know that NCR is always going to be smaller than NPR, right? Or basically always, we'll see, right? Because this r factorial down here increases the size of the denominator or the bottom number, and when you increase the size of the denominator, your overall number, of course, is smaller, right? But so combinations are for when order is not important. Combinations for when order is not important. And then permutations. Permutations is for when order is important. And at Calais, I know before you asked me specifically about, say, questions involving decks of cards, like one of those ones that you had to do on your assignment, and I sort of beat around the bush a little bit and didn't really get to those, right? But the reason is because most problems involving decks of cards do not use permutations; they actually use combinations, right? Because say if I was dealt the following 5 cards as a hand, right? These ones, if I'm dealt 10, queen, king, 3, 7, like that, that's the exact same as if I was dealt them in this order 7, king, 3, 10, queen, right? The order doesn't matter because I can, if you're holding a hand like this of cards, say it's 5 card draw or whatever, right? Or triple draw low or some sort of nice poker game that you use for 5 cards, you can rearrange them in your hand all you want. And it might be giving a tell. Other people might be able to glean a few things about what your cards are, maybe, or how they relate to each other at least. But the actual hand doesn't change, right, depending on the order of them. Whereas in other ones, like if we look at questions, a very common type of one will be, say, members on a sports team, right? So if it's a sports team where there aren't defined positions, like, I don't know, a dodgeball team, I guess dodgeball doesn't have positions, does it? And it'll say, like, how many ways can the coach pick 6 students out of 10 students to make this dodgeball team? Well, that's going to be 10C6 because you're just choosing the 6 of them and it doesn't really matter where they're playing. But if they're playing another game where the position does matter, like, say, baseball, right? Then how many different ways can a coach assign 6 people out of 10? Well, that would be 10P6, right? Because then, depending, are they first base, or the second base, are they outfield or the midfield, right? All those different positions are going to be, it's going to be different where we assign those people, right? So anyway, yes, combinations for when order is not important. Permutation is for when order is important. Now, as a way of introducing this a little bit, I want to go down through one of the examples in your textbook, and I'm going to pick these 2 examples here on page 114, just to go down through really briefly. So it says Tanya is the coach of a pole push team that consists of 9 players, 5 male and 4 female. Okay. In each competition, teams of 4 compete against others to push their competitors out of a circle. The team that is successful wins. Okay, sure. So how many different 4-person teams does Tanya have to choose from for an all-male competition? Now I'm not gonna let's zoom in a little bit here because I'm not gonna go down through. Not going to show you Tanya's result. I'm just going to do it out kind of on paper over here. Right? So let me slide this guy over here. Oh, no. That's perfect. There we go. Okay. So then this is page 114. This is going to be an example of combinations. And this is going to be part A. And I'm just going to sort of walk you through how we're going to go about doing this one. How many different 4-person teams does Tanya have to choose from for an all-male competition? Okay. Well, in this sport, I gather the positions don't matter, right? Choosing one person first and another person second is the same as flipping the order. It doesn't really matter. So we are going to be using combinations, as the order doesn't matter, right? You see here. So then teams of 4, so teams of 4 compete. So we have 5 males in total. Choose 4 for a team. So how are we going to go about doing that? Well, we're going to do 5 choose 4 is the way I read it, and that's the way that makes a lot of sense to read it. 5 choose 4. I know it's combinations. It's not the word choose literally, right? So it's not 100% technically correct to say this is 5 choose 4, but I do like to use that verb to think about what we're doing here. All right, so that's going to be a 5 factorial over a 4 factorial times 5 minus 4 factorial, right? So that's going to be a 5 factorial over 4 factorial times 1 factorial. And how can we write this out to expand it? Well, we might not need to expand it because you might, from the other questions that we've done, you might already understand what I'm about to do here, right? Now I got rid of the 1 factorial because 1 factorial is 1, of course. When we multiply by 1, nothing happens. So then this 4 factorial is going to cancel with that one, and we're going to be left with 5. Well, how does that make sense? How does it make sense that if there's 5 people, there's only 5 ways to choose 4 of them? Well, it's because when we're doing combinations, right, 5 choose 4 is going to be the same as 5 choose 1. And why is that? Well, because if we're choosing 4 out of 5, kind of what we're doing is we're choosing 1 to be the person who doesn't play, right? If we're choosing 4 out of 5 to play, that's the same as choosing 1 person to not play. And since the order doesn't matter, 5 choose 4 will be the same as 5 choose 1, right? And we'll see an example of that shortly. One of your book questions does ask you to sort of derive that property, but it makes total sense when you think about it, right? Like say 10 choose 9. Well, how many ways can you do that? 9. 9 ways because, oh, 10 ways, sorry, 10 ways. 10 choose 9. There's 10 ways to do it because there's 10 people. That could be the 1 person not chosen. Right? Anyway, so that's all we have to do there for A, right? For B, how many different 4-person teams does Tanya had to choose from with 2 males and 2 females for a mixed competition? Now this is a good example. The one reason why I wanted to do this one, because this is an extremely common situation that you're going to see a lot, where you have sort of multiple cases that you have to combine together, right? So how do we choose 2 males? Just to fit, just the first part first. Well, there's 5 males. We're going to pick 2 of them, right? Then and we need to do something else. Now remember in math, right? If we're going to do an and for these ones, we're actually going to be multiplying, right? We're going to multiply because it's like probability, right? If we had to do if we had to do 2 situations here for choose, we're going to multiply the 2 of them together. So then we have choosing 2 females. We have 4 females, so then there's going to be a 4C2 over here, right? And we're going to multiply these 2 together. So that then is going to be the same as, well, we know that 5C2 is going to be 5 factorial over 2 factorial 5 minus 2 factorial. That's going to be multiplied by the next one, which is 4 factorial over 2 factorial 4 minus 2 factorial. Right? And I'm just going to go down the page now like a proper math teacher, showing you exactly how to write it out. Not an improper math teacher, which is more of what I am. 5, I'm going to call this 5 times 4 times 3 factorial on top. And that's going to be over 2 factorial 3 factorial. Just going to expand these a little bit from the get-go, just so we have a bit of an easier time on the next step. Right? And now we see this 3 is going to cancel with this 3. This 2 is going to cancel with this 2 factorial. And what we're going to be left with is 5 times 4 over 2 multiplied by 4 times 3 over 2. Right? We can cancel that there and that and call that a 2, that and that and call that a 2, like so. So we can now say that this is 5 times 2 times 2 times 3, right? Which is going to be 60. 10 times 6, 60. There we go. Right? So that's all we had to do then to do the NCR formulas, right? And as you see here, NCR is very, very, very similar to NPR, just as a formula. The real meat of this unit, like the real important part that you had to understand, is how we go about determining when we use one versus when we use the other, right? So the stream is already going. It's not starting soon. But let me now just scroll down to the next page that I'm going to use, and then we'll flip back on over to my other view here. Okay. There we go. So now this is page, what page is this? 118. So this is page 118 in your textbook. I'm going to do a few of these questions here now. So this is Math 3101A Unit 2. Page 118. One reason I want to do these ones is because it does bring up, like I said, the permutations versus combinations, and when we use one and when we use the other, which is, like, I can't overstate that is going to be one of the biggest topic for the test in this unit, basically, is when do you use permutations, when do you use combinations. Excuse me. So Joe has a choice of 4 flavors of ice cream for his 2-scoop sundae: vanilla, strawberry, chocolate, and butterscotch. Delicious. List all the permutations for a 2-flavor sundae. All right. So it's asking us to list the permutations for a 2-flavor sundae. Yeah, sure. Why not? So it's going to be vanilla strawberry, vanilla chocolate, vanilla butterscotch, right? And it's going to be strawberry vanilla, strawberry. Oh, I guess we can do. Can we repeat? Can we repeat? That's a good question. That's a good question if we can or not, actually, for this question. Um, so strawberry vanilla, strawberry chocolate, strawberry butterscotch, um, chocolate vanilla, chocolate strawberry, chocolate butterscotch, butterscotch vanilla, butterscotch strawberry, butterscotch chocolate. Right? And then you know what? I'll go ahead and do the double up. All right, so that's all the number of permutations, because here the order does matter, right? Because we're saying here that, say, vanilla on top and strawberry below is different than strawberry on top and vanilla below. That's the difference. That's why these are the permutations, right? So then for B, which ones are the combinations? Well, we have all these first ones: vanilla, strawberry, vanilla, chocolate, vanilla, butterscotch, and vanilla, vanilla. But then now we're going to leave out this SV. And why are we going to leave out that one in the next column? Well, it's because, like I just said, it was already taken care of over here. And they're different when they're permutations, but when they're combinations, they are not. And we'll notice now that as we go along, obviously each of these rows is going to get one smaller each time. Because now chocolate vanilla, well, we've already covered that one. Chocolate strawberry, we've already covered that one. So this is just going to be chocolate butterscotch and then chocolate chocolate. And then we've already got butterscotch combined with all 3 of the other ones. So our final combination is just going to be butterscotch, butterscotch. Right? So as you see here, we've got 16 permutations for this situation. But we have only 4 plus 3 is 7, is 10. Yep. 10 combinations. That's all. How is the number of 2-flavor permutations related to the number of 2-flavor combinations? Explain. Well, like we were just saying, right? Because combinations, you can't switch the order. These are going to go down each time, right? So this one is 4 times 4. Well, this one is 4 plus 3 plus 2 plus 1, right? Now, question two down here is much more like the ones that you're going to be asked, right? From a group of 5 students, 3 students need to be chosen for a car wash committee. Wait, hold on. So 2A then, how many committees are possible? Well, the number of possible ones is just going to be 5 choose 3, right? Or 5C3, because we're not told that, say, one position is any different than another position in the committee, right? So it's going to be 5 factorial over 3 factorial, 5 minus 3 factorial. It's going to be 5 times 4 times 3 factorial over 3 factorial, 2 factorial, which is, those are going to cancel. It's going to be 5 times 4 over 2, which is going to be 10. So there are 10, right? For a group of 5, 3 students. How many committees are possible if only 2 students are needed? What's going to happen? What's going to happen if only 2 students are needed? Do we have a prediction for that one? Right? Based on what we did previously, do we have a prediction? Well, let me show you. This is going to be 5C2. I can tell you right now what this one is going to be, and not just because I've done these questions before, but because I did that last question. Watch what happens. Look at that. It ends up being exactly the same as this one. How strange. That's going to cancel with that, like so. And then we are going to have 5 times 4 over 2, which is 10 again. Why that? Why are these the same? 5C3 and 5C2? Well, it's just like what I was saying earlier, right? That if we're choosing 3 people to do something out of 5, well, it's kind of like we're choosing 2 people not to do it, right? It's sort of the same thing. And over here, we're choosing 2 people to do something. Well, it's kind of like we're choosing 3 people not to do it. So it's actually what determines the answers here is basically what the difference is between this term and the maximum, right? Or this one and the middle one, and the minimum, sorry, right? The difference from the max or the difference from the min, if those are the same, then we actually end up with the same number. That's why I say 5C0 or 5C5, those are going to be the same. 5C4 and 5C1 are going to be the same, and 5C2 and 5C3 are going to be the same. Okay. Question 8 then. I do want to do question 8, because question 8 is, like I was talking about, one of those ones that you're going to be picking for these ones, right? So then for question 8, actually I'll do this one in blue, seeing it's over and underneath another one over here. Question 8. It says, Connie's softball team has 15 players. How many ways can the coach choose a starting lineup of 9 players if Connie must be the pitcher? Okay. So does the question involve permutations or combinations? Explain. Well, it would involve combinations if every position on the team was the same. In softball, the positions are not the same. Right. So it would involve combinations if every position on the team was the same. In softball, though, the positions are different. Therefore, we have to use permutations. Right? And then for B, another reason I wanted to do this one is because 8B is also very similar to some of the ones that you're very likely to see on your test or anything like that. In 8B, it tells us to go ahead and solve the problem. Well, how are we going to do that? Connie's softball team has 15 members. How many ways can the coach choose a starting lineup of 9 players if Connie must be the pitcher? Well, how do we account for that Connie must be the pitcher part? It's actually a lot easier. It's actually a lot easier than you might think, right? Because this is a very common thing to see an order of combinations or permutations where certain parts of it are fixed, right? And I think you've seen some examples of that already. Like there's a one question, I believe, in one of your activities. I think it's the one that I'm waiting for you to submit, I believe, where it says like, not I'm waiting for you to submit, the one that you haven't submitted yet, I should say. I'm not really waiting, not really rapturously sort of waiting on any math work to be submitted. I'll tell you that. Yeah, so I mean, submit it whenever you get it done. Obviously, just is at your own time. But like, there's a one where it's the word Saskatoon, right? And like, how many ways can you reorder the word Saskatoon if there has to be an S at the start and an N at the end, right? But that's not really all that strange, because all we're doing then is having one fixed S at the beginning, one fixed letter at the end, and then the rest of them change. So all we're doing is kind of subtracting 2 letters from it in total. So here, right, if Connie has to be, if there's a team of 15 players with a lineup of 9 and Connie must be the pitcher, well, how many players in total do we have left for the other positions? Well, we have 14 left, right? Because Connie's already assigned to one specific position. So we have 14 players left. Then how many positions do we have left? Well, it's going to be 8, right? Because one of the 9 positions is just already taken up by Connie. So the only difference between, Connie having to be the pitcher is that we're just going to reduce the total number of players by 1, and we're going to reduce the total number of positions by 1. That's it. So instead of 15P9, which is what the question looks like it should be from the start, it's actually going to be 14P8. And that's just because Connie is already spoken for, and the pitcher position is already spoken for. So this goes down by 1, and this goes down by 1. So then we know that we have 14 factorial over 14 minus 8 factorial. Because this is permutations, therefore we don't actually have the r factorial out here, which is going to be 14 times 13 times 12 times 11 times 10 times 9, 8, 7, 6 factorial. Boy, I'm really crammed that one on there. You know what? Let me write that. Let me write that line again. Let me scratch that one, reverse it. It's 12 times 11. We're not really reversing it. That's just a line from what movie was that? That was Gene Wilder in Charlie and the Chocolate Factory, right? Yes, that's Willy Wonka. Scratch that, reverse it. That's where that's from. Divide by 6 factorial, right? Because 14 minus 8 is 6. And the 6 factorial is going to cancel with this one, and we're going to be left with a whopper of a number. Now, if you look in the back of your book, the back of your book might use combinations here instead of permutations. I haven't checked, but you definitely should use permutations here because we know that the game is softball, and we know that in softball, each position is different, right? If we have, Jimmy playing shortstop and Timmy playing, third base, that's different than if Jimmy plays shortstop and Timmy plays third base, right? They're all playing, but the positions do indeed matter. And that is a whopper of a number. Holy moly. 121080960. Boy, oh boy. That is 121 million ways that you can organize these 8 of 14 players into 8 different positions in a game of softball. Boy. See what I mean about these numbers getting big fast? They get big. They get big in a hurry. Now, there's one more that I wanted to look at here, which is question, question 15. I did also want to show you as well, really briefly, just how we go about doing a question like number 15. Because question 15 has a small wrinkle, and it is something that you're definitely going to see ones like this as well. So I'm going to do question 15 over here down below. So let's cram question 15 in here on this part of the page. I'm going to zip over to this display and then zoom in a bit so we can have a bit more room. I'm going to go ahead and do, I'll just probably do 1 for question 15 just so you can see how this is done. And then hopefully you can extrapolate this bit to any of the other questions that you have that work the same way. This is going to be NC2 equals 15. Now, how do we go about doing these ones, right? Because, well, we're not told what n is, so we can't go ahead and plug it in like this, right? because we don't have what it starts off as. But we can still solve this question just fine. So what we're going to do is we're going to write out the formula, right? But we're going to leave this 15 over here, and we're going to turn this part into the part that looks like that, right? So what we're actually going to have is n factorial over 2 factorial n minus 2 factorial equals 15, like so. Right? Now, this part down here is actually super duper clutch. Like, it's really important that we have this part here on the bottom, or we wouldn't be able to solve this question at all. Because we remember now from some of the previous lessons on this topic that n factorial is the same as n multiplied by n minus 1 multiplied by n minus 2 factorial, right? Because this keeps on going downwards. And then on the bottom, then, we have our 2 factorial times our n minus 2 factorial, and that's going to equal 15, like we were told over here, right? So then what we end up with, once this cancels with this, we have n times n minus 1 is going to equal 30, actually, because I just multiplied this 2 across here, because I'm running out of space a little bit. Then what we have is n times n minus 1 equals 30, or what we can call this is n squared minus n minus 30 equals 0, like so. And now what do we have? Well, now we have a now we have a bit of a mess. Now we have a bit of a mess. Why? Because this is now a quadratic that you had to solve. Now, there's loads of different ways that you can go about solving quadratics like this. Unfortunately, Calais, a quadratic like this is the first topic of the grade 10 academic, and you haven't done that one, at least not with me. Now, you do have credit for that course, so I know you've done that in the past. I just don't know how recently it was, and I don't know if you remember it right now. But you will need to brush up a little bit on how we go about solving these guys, right? But one way that always works is the quadratic equation. Another way that always works is to think, well, we need two numbers that add to give us -1 and multiply to give us -30, right? So if we we know that we need x plus y has to be -1, because that has to be this coefficient there, and we know that x times y has to be -30. Well, what things give us 30, right? So 30 can be 1 times 30, 2 times 15, 3 times 10, 4 doesn't work, 5 times 6. Hey, there we go. 5 times 6 will do it for us. I know I'm sort of writing this quite small here now because I started running out of space, but we do have enough space to finish this, right? So now I know that it's going to break down into a -6 and a +5. So this is going to be, the way this one's going to factor is into n minus 6 times n plus 5 equals 0. So now we have to pick the numbers that would make this true. So what I've done here now is I'm factoring. So we need the factoring there from that one, right? So now we can say, well, what values of n would make this case true, right? So either anything times 0 is 0, of course, right? So either this whole bracket needs to be 0, or this whole bracket needs to be 0. For this one to be 0, n would have to equal +6. For this one to be 0, n would have to equal -5. Okay? So from the factoring part, our answers for this will be either a +6 or a -5. And if we look back here, remember what we're doing is some number choose 2, right? So if we have, say, 6 choose 2, well, that makes sense. We could do that. How about -5 choose 2? Well, a -5 doesn't make any sense here. It doesn't actually work because we can't use a negative in this sort of a situation. So we know then that the answer is 6. So 6C2 is 15. Now, like I said, that is a topic from a previous course that you didn't do with me, but I gather you have done in the past. So hopefully those are familiar to you. If they're not, do please let me know, right? I haven't gone over that in extensive detail and like how we do that factoring, but Calais, if you need that, just let me know and I will go over those. For now, though, that'll be the end of the first section of the combinations. So I'm going to do some radicals stuff here now with NPVs and solving. So I'm going to look a bit at questions 9 and question 11 on page 228. Right, so these are going to be, I'm going to go down through these ones fairly quickly here. Right, so this is going to be math 2101B, unit 1. Now then, Betty Ann, if you're watching the stream and want me to do any of these questions, you can mention in chat which ones you'd like me to get to. Otherwise, I'm just going to pick a scattered few of these ones and go over them. All right, so let's do the harder ones. Let's do C and D here. So C is 3 outside of root 7x plus 3. And notice that the plus 3 is outside the root, and that equals 12. Now we know we will eventually have to square the sides, but if there are other terms on the same side as the root, then once we square it, we're just going to end up with a huge, massive load of work to get to, and we're not really going to get any further ahead. So what we have to do first is we have to get rid of these other terms over here. So this is going to be 3 root 7x equals 9, because I've subtracted a 3 from each side. And now I could go ahead and square right away, but I'm going to get this 3 out of here first. So I'm going to divide both sides by 3. It's going to be root 7x equals 3. Now I'm going to go ahead and square both sides. 7x equals 9. And now I'm going to get x's value is going to be 9 over 7. And that is the final answer here. But now we're not quite done this question, right? Because from the start it said state the restrictions on x, then solve each question. Now the restrictions on x are not, it's not once we get to the end here. Now these are a bit of odd questions to ask for restrictions on x, because to be very pedantic, right? Here x has a definite value because we've got one variable and we've got an equation. So really, what are the non-permissible values for x? Well, if you want to get really technical, there aren't any, because x has to be 9 over 7 for this equation to be true, and no other value can even be inserted here. But we'll play the game. We'll state the restrictions on x, as if this equals 12 wasn't here, if this was an expression instead, and x could take any value, then there would be some values that x would not be able to be. But anyway, that's just, it's a little bit pedantic to draw that point, but I do think it's relevant to say. But the NPVs here, well, we know that we can't take the root of a negative number, right? So if we can't take the root of a negative number, x here has got to be greater than or equal to 0. Because remember the rules, right? The rules for NPVs are can't divide by 0. Can't divide by 0, and you can't take the even root of a negative number, like so. All right? So we just have to make sure that what we're doing, we're neither dividing by 0 nor taking the even root of a negative number. Right? So here this is an even root because it's square root, so we can't have a negative under there. Of course, if we had an odd root, then we could, right? If it was a cube root, because we can't get the cube root of a negative. So D is going to be 1 over 4 root of 5x minus 2 equals 6. One reason I want to do this one as well is because notice the difference, right? Here, the symbolic root is not over the plus 3. Here, the symbolic root is over the minus 2. And that is, of course, an essential difference here. I could go ahead and square right from the start and call this, 1 over 16 times 5x minus 2 equals 36. But I ain't going to do that because that's just making more work for myself. So what I'm going to do is I'm going to get this left side to be just the symbolic root, right? So this is going to be just 5x minus 2, all root, and then I'm going to multiply both sides by 4. This side's going to become 24. And then I go ahead and square these. It's going to be 5x minus 2 equals, I don't know what 24 squared is off the top of my head. I'm going to go find out. 24 squared, 576, right? So then 5x is going to be 578, and then x is going to be 578 over 5, which is whatever. 115.6. Oftentimes we don't write those as decimals, but seeing it's a rounded decimal to one decimal place, I figure what the hey, let's go ahead and put that in there. Actually, yeah, I'm not going to do question 11. No, I mentioned I was going to do question 11. I don't think so. I'm going to do question 10. Question 10. Oh, right. My MPVs first. Boy, see? Almost ended up losing some marks off my own activity if I didn't do the NPVs over here. So the NPV for this question, well, again, right, we can't divide by 0, but there's no dividing by the x happening here. So we can't take the even root of a negative number. So there is an even root going on here. So I know that 5x minus 2 has got to be greater than or equal to 0. And now remember from before, right, that a greater than, less than, or whatever sign, in algebra, we treat it just like it's an equal sign. Pieces move around it just the same. So now we're going to call this 5x has to be greater than or equal to 2, right? Because I've added a 2 to both sides. I'm going to divide both sides by 5. 5x is greater than or equal to 2 over 5. And that's your NPV for this question, right? It is a small little part, but I mean, that's, if this question was worth 3 marks, this part is worth 1, right? 1 out of 3. So it's important. It's important to do those because you don't want to be just losing those marks willy-nilly, right? So let's do a few others over here. Yeah, how's about let's do 10. Let's do 10B and C. 10B. We've got this is a cube root now, which is one reason I wanted to bring this one in. And remember, the 3 needs to be down inside the little crook there, right? I mean, I prefer fractional exponents to symbolic roots, but we'll play the game that your textbook is presenting. 7 minus 2x, then the plus 1 is here outside, equals negative 3. And like I mentioned up here, we always get rid of the stuff that's outside first, so we're going to subtract the 1 from both sides. We're going to have the cube root of 7 minus 2x is equal to negative 4. Now we're going to cube both sides, right? Now, of course, cubing a cube root just gives us 7 minus 2x, like so, right? And what's cubing negative 4? Well, negative 4 times negative 4 is positive 16. Positive 16 times a negative 4 is going to be a negative 64, like so. I'm going to switch the sides of these two pieces. I'm going to have 7 plus 64 is going to equal 2x over here, right? So 71 equals 2x, or 35 and a half is equal to x. Right? And it's totally fine to have a decimal answer, right? But what are the NPVs for this question now, for 10B? Well, we can't divide by 0, right? But is there any dividing by x going on here? There's not. Can't take the even root of a negative number, but there's no even root here, right? There's just a square root. No NPVs. There's no restrictions on x in this one. X can be literally any value, right? Because we can indeed take an odd root of a negative, just like we saw over here, right? When I cube both sides, this still ended up being negative over here because it was -4 times a -4 becomes a positive. Then we times it by a -4 again, goes back to being negative. All right, so sometimes NPVs will be none. Now you do still need to specify. If question 10b was on a test like that and you didn't write down NPVs none, I would have the doc you say 1 out of 4 or 1 out of 3 from that question, right? Because you do need, when it asks for it, you have to indicate it. Question C, so that is the square root of 4 outside of 3x plus 12 equals 6. Now here, what am I going to do with there being a multiplication inside here? Well, guess what? Like, basically nothing. Basically nothing at all. I can just go ahead and square it from the start, right? Because here now, we're at a position just like we were here, just like we were here, and just like we were here, in that one side of the equation is a radical, and the other side is one term, but it doesn't always need to be one term. But the other side is not a radical, right? But over here, we just have one whole radical. So I'm going to square both sides. We're going to get 4 outside of 3x plus 12 equals 36. Now I could have from the start here, I could have gone and multiplied. I could call this 12x plus 48. I could indeed, right? But I'm not gonna. I'm not going to because I'm just going to keep doing what it shows over here. Or also, I could factor a 3 out of this, and I could call this 12 outside of x plus 4. I could do either of those. But I'm going to just carry on from what's written here, doing basically the most obvious steps, I suppose, or as few steps as possible. So now I'm just going to divide both sides by 4, and we're going to get 3x plus 12. 36 divided by 4 is going to be 9. Right? And like I said, if you notice that you can factor a 3 out of both here, I could go ahead and divide both sides by 3 here now as well. Right? I totally could do that. And I could call this x plus 4 now equals 3. Right? Or I could call it, which was going to be x equals -1. I could call it that. Right? Or from right here at the start, I could have now called this 12 outside of x plus 4 equals 36, which would have got me to x plus 4 equals 3, which would get me to x equals -1. Or from this point, right, there were loads of different ways I could have gone here. Or from this point, I could have called it 3x plus 12 equals 9, like I did there, and then subtracted 12 from each side and had 3x equals -3, and then x equals -1. Either way, you will see, of course, that the workings are going to get you to the same place in the end. So that's what I say a lot about these algebra questions, is as long as every single step you're doing is consistent with the rules of algebra, then what you're going to get in the end is going to be correct. And now what are the NPVs for this question, for 10C here? Well, I know that everything that's under the root has got to be greater than 0, greater than or equal to 0, right? So 4 outside of 3x plus 12 has to be greater than or equal to 0, right? And I can divide both sides by 4. How about I just divide? Yeah, let's factor it like I did over here, right? And call this 12 outside of x plus 4 is greater than or equal to 0, which means x plus 4 is greater than or equal to 0, because now I've divided both sides by 12, right? Which means x is greater than or equal to -4. Right? Now, there's lots of different ways that we could have shortened this part up a little bit, but I think that this is probably still a very clear way of going through it. Now, none of these had dividing by 0. In fact, neither 9 nor 10, neither of those have any dividing by 0 to make NPVs. But this is just sort of the way that we're going to go about answering those questions. Okay? Now, to bounce on back over to my initial page, I do have one other small topic that I want to get to today, which is, like it says up there, going to be word problems for angle properties review. So this one is Renetta's course. So I'm going to go ahead and do, let's see, what page is this? This is page 271 in your textbook. We're going to go back over to this one here. All right, so I'm going to do question 4. So this is going to be Math 1102B. This is, I believe, Unit 2. It's going to be page 271. And this is going to be question 4. Question 4 tells us, race cars have built-in roll cages to protect drivers. The back of one type of roll cage includes bars in the formation shown. Does X need to measure for bars A, B, and C, D to be parallel? Okay, so let's draw out our diagram. Right, when in doubt, draw it out. Or even when you do know how to do it, draw it out anyway. Right? Doubting or not, go ahead and draw that mother out. So, I'm going to have a line here, line here, line here, one that meets up sort of in the middle this way, one that meets up in the middle kind of this way, and then one that crosses this side over there. There we go. Okay, cool. That's pretty much it. A little bit off, but whatever. Like I say, the way the diagram is drawn doesn't necessarily have to correspond to what the angles are on. Now those two ones are parallel, and we know this angle here is going to be 47 degrees. What does X need to measure? Where is angle X? Oh, X is, okay, it was hard to see that, isn't it? It's a bit tough to see, but the X is right there, yeah. It's hard to see with that background that they've got on that picture. So X is there, and this is AB up here, and this is CD down here. What does X need to measure for bars A, B, and CD to be parallel? Well, if this is parallel with this one, right, we know that this line here, from there to there, or this line that I'm going to, I'll add a bit of green shading to the line. Right? It's hard to see on the camera. Hard to see on the camera that that is green shading. There we go. There we go. That's good. So green line. Okay, so green line is a transversal between lines A, B, and C, D, right? The red circled ones, those are same side interior, so they must add to 180, right? So we know that X has to be 180 minus 47, so X has got to be 133 degrees. So what does X need to measure for it to be parallel? 133 degrees. Sorted, right? That's it. All you got to do for that one. Easy peasy. Now, if we look down, I'm going to do number 6 next. And then, yeah, so that'll just be 2 quick examples, Renetta, for these ones. You haven't asked specifically for any of these, so I thought I would just do a few of these examples so that you would have them to take a look at while reviewing for the test. So number 6 then, a Tudor style house has half timbering, which is exposed framing. I lived in a house in the UK briefly that had exposed timbering, sort of like this. Not on the outside as obviously as this, but like on the inside, these big rough hewn timbers, like supporting the roof and stuff. It's really gorgeous. It's a very appealing sort of construction on the inside, especially like these huge like old heavy doors, and the ceilings were a bit low though, because I guess people were shorter in Tudor times. Anyway, has half timbering. Are the 4 vertical lines in this section of half timbering parallel? Give reasons for your answers. Okay, so let's go ahead and draw out a reasonable facsimile of this diagram. It's going to go from this corner up to this corner. Now this is 49 in here, 49 degrees, right? This is 131 degrees here. This is 131 degrees here, and this is 49 degrees here. So it's asking us, are the four vertical lines in the section of half timbering parallel? Well, we know that if they were parallel, right? Um, right, so therefore the two middle ones are indeed parallel, and we know that because, right, this sort of forms a Z shape, and we know then that um, this angle there and that angle there should be equal if they are parallel, and they are indeed equal. Therefore, those two ones are parallel. Now, do we have, how can we tell? How can we tell these ones in the corner, this one over here and this one over here? How can we tell if those are parallel? Well, unfortunately, in this section, we actually don't have enough information to tell because we haven't been told any angles about the leftmost timber, and we haven't been told any angles about the rightmost timber. We've only been told angles about these two middle ones. So we actually don't have enough information to determine if this one and this one here are parallel. Because look, like this Z shape here, well, we're not given that angle, we're not given that angle. We're actually not even given these corner ones, right? We're not told, if we were told this was 90 and this was 90, well, then we would know. Then it would be parallel, right? But we're actually not told any of that. So we have to say we don't have enough we don't have enough info to tell if those ones are parallel. And that's just a totally fine result, right? Um, that's just a totally valid result that we can get. That sometimes you're not going to have enough information to tell, and in those cases you should write it out on the paper there. Okay. So are the four vertical lines in the section of half timbering parallel? Well, the two middle ones are parallel with each other, and the two ones on the outside we actually don't know. We don't have enough information to be able to tell. Okay. So those are, I think, some fairly good examples, Renetta, for how you're going to be going about doing those questions. Now, in a few seconds here, I'm going to have something a little bit different is going to happen on stream here now. Now, it's been very, very quiet in chat today. I gather, that could be because Newfoundland has only recently just opened back up a little bit, right? So, we've ratcheted down to level 3 on our sort of COVID-19 alert. which means that some businesses, hairdressers, other places like that, are now reopening so that people can go out under some restrictions still, but people can go out and resume some parts of normal life, I suppose. But the distance teaching here, like this, the daily stream and all that, this goes on. This is going to be going on until, like I said, my stream is going to go on until the end of June, for sure, and then potentially, now, potentially we're going to be returning to doing online teaching again in September, which means I may be back to reprise my role as NL Math Man in season 2. All right, maybe we'll have a little bit of some new twists or something like that for season 2 come the fall. But I'm going to do something a little bit different here now in a second. Now, this is partly because of Twitch and Twitch's restrictions. I didn't know that between when I used to stream Hearthstone, which I did for a while, and starting doing this math tutoring stream, Twitch changed some of its functionality, unfortunately, and you can no longer upload videos to Twitch unless you're an affiliate, right? And I'm not an affiliate on this channel, and I probably won't be because there's not a whole lot of people, just randomly popping in to watch math tutoring streams. So I don't know that we're going to get the number of followers or the number of chatters necessary for me to ever become an affiliate on this channel, which is fine. Like, I'm doing this for a different purpose. It's not to become Twitch famous. That's Twitch famous for math tutoring, boy. But anyway, I do want to have some of my best streams available to watch as highlights of my stream. And unfortunately, once they're taken down after 60 days, I have no way of putting it back up. So I'm going to run, as soon as this is over, I'm going to take the stream down for about a minute or two, and then it's going to come back up. And when it comes back up, it's going to be a rerun. It's going to be a rerun of day 2 of my tutoring stream, right? And then we're gonna watch. Well, I'm gonna watch anyway. I don't know that anyone here is watching it with me, but we're gonna watch the first 20 minutes or so, and then I'm going to save that one as a highlight. I will then go and delete that video afterwards, so it's not gonna like clutter up my videos section or whatever. But anyway, if that's going to enable me to make a highlight of a day that is now gone, but I meant to make a highlight of before, basically. I hope that makes sense. So thanks for being here with me today for the live portion of the stream. Like I said, I'm going to take this down, and then very briefly, I'm going to come back up with a pre-recorded video, right? I will be still in chat, so if anyone's, confused as to what's going on, I mean, I guess you probably don't see this part of me talking about it, but you can send a message in chat, and I'll still be here and respond. But we're going to watch about 20 or so minutes of what I think is one of the best streams that I've done so far, just because of the I don't know, the delightfully raw sort of comedy at the beginning, and I want to make a highlight of it, and this is the only way that I can upload it to Twitch until I'm an affiliate, which is probably not going to happen. Okay, so thanks for being here with me today, and like I said, we will be live again momentarily. No, actually not live. We'll be in a rerun. Momentarily. Hold on. Okay.